Good morning, everybody, and welcome back to Calc 1. Took me a second to remember what class this is. Plan for today, we're going to wrap up Standard 10, and if we have time towards the end of class, start talking about Standard 11. We've got my usual office hours for the next few days. Today, Wednesday at 11 and at 1. Tomorrow at 1. And I put up a web work over the weekend, homework 15. It will be due on Friday. And on Wednesday, we will have a quiz over Standard 10. How are y'all doing this morning? Glad y'all could make it. It's a gloomy day out there. It's a Monday after fall break. It's 7:45 a.m. Let's do something fun to kick things off. So before I jump in, I thought it would be fun to kind of do a little bit of review and then see something a little bit new. If I were to give you y equals x to a constant power, x to the a, so something like x squared or x cubed or x to the 10th power, and ask you to differentiate that, what would you get? Anna? Yeah, you'd use the power rule on that. You have x to the power of a constant number, which in order to differentiate, you would get a times x to the a minus 1 by the power rule. On the other hand, if I gave you a to the power of x, so this time we would be looking at something like an exponential function, like 2 to the x, or 3 to the x, or pi to the x power. Nora? Yeah, it's going to be natural log of your base times a to the x power. So something to keep in mind is when your x is in the base, the thing you're raising to a power, you use the power rule. When your x is in the exponent, though, you use the exponential derivative rule. Didn't really have a name. If it had a name, I'd call it the exponential derivative rule. All right? You all are old hats at these functions. So let's spice things up a little bit. What about y equals x to the x power? Well, what do you think? Do we use the power rule, or do we use the exponential derivative rule? Franklin?
Does it matter? Like, can you just choose one?
Well, if we chose one, if we did the power rule, we'd get y prime equals x times x to the x minus 1. It'd actually just be x to the x again. Funny enough. If we did the exponential rule, put these in the wrong column, we'd get y prime equals natural log of x times x to the x. Are those the same? Franklin?
No.
What do you think? Does it matter which rule we use?
Probably.
Yeah, I would say so. If it didn't matter, we would expect to get the same answer either way, but that does not appear to be the case. So here's the fun thing. I actually lied, Franklin. It doesn't matter which one you use, because using either one of these would give you an incorrect answer. You can't use the power rule because the power rule requires that your exponent is a constant. You can't use the exponential derivative rule because that requires that your base is a constant. How do we differentiate this bugger? Hey,
Chain rule.
cool. What's our inside function?
X.
All right.
Like
Uh,
the base X. And then our exponential X is our first.
Okay, if g of x is our outer function and h of x is our inner function, tell me what I should write for h of x.
H of X is the inside, so X, yeah.
And what's g of x?
X, or the exponent X. I'm not sure how you want to write that. Alright, well, yeah.
Like that?
Yeah, sure.
Cool. So if I take g of h of x, well, h of x is just x. So that's just g of x, which, I don't think then g of h of x is our original function. Chain rule has gotten us out of a lot of sticky situations. It's actually not super helpful this time. James?
Limit definition?
No. I mean, yes, but also no.
Okay.
If you want to plug this into the limit definition, technically that should work, but have fun with that. Can't believe none of you are suggesting the most obvious thing. We're going to take natural log of both sides. Come on, isn't that obvious? That's a joke, in case you didn't know. Why? You can use a nice property of natural logs here to say if you're taking natural log of something to some power, we can take that power and move it down in front to get natural log of y is equal to x times natural log of x. And now, I want to differentiate both sides of this equation. I'm going to differentiate with respect to x, natural log of y, and then differentiate with respect to x, x times natural log of x. Because if these two expressions are equal to each other, then when we differentiate each side, they should still be equal. Let's start off with the right-hand side. What rule would we have to use to differentiate x times natural log of x? Yeah, Charlie?
Need a product rule, right?
Well, it looks like a product to me. All right, what would the product rule tell us we would get then, Charlie?
The first times derivative of the second would be x times 1 over, I don't know, 1 over x, sorry.
Yeah, derivative of natural log is just 1 over x
Plus 1 times n of x.
plus the derivative of the first times the second, which when we simplify, we'll actually get 1 plus natural log of x. How about on the left-hand side? We differentiate natural log of y with respect to x. Good golly, small. Martin?
Would it be 1 over y prime?
1 over y times a factor of y prime? What sorcery did you just do?
Best.
Yeah, you guessed. That was a good guess, it's correct.
Yeah.
What made you guess such a thing?
I just replaced the variable, and then because we're taking the derivative of y in respect to x, it has to have the y prime or the dy dx.
Ooh. So in other words, it sounds like you did some implicit differentiation. Where if you remember, when we were doing implicit differentiation back in Standard 8, we were looking at things like, oh, we have an expression in terms of x and y that we want to differentiate, which would give us something like 2x plus 2y times a y prime, and then we would probably solve for y prime or something. Same's going to be true here. The derivative of natural log of thing is 1 divided by thing. We saw back in Standard 9. But then if we use the chain rule, Aiden, I also lied to you, chain rule is actually useful here to do some implicit differentiation. If we use the chain rule, we need to multiply by the derivative of the inside expression, which in this case is a y, which will give us our y prime term. So what we end up with is a lovely expression of the form y prime over y is equal to 1 plus natural log of x. So if y prime over y is 1 plus natural log of x, what would y prime be? If we wanted to get y prime by itself? John?
Y plus y times the natural log of x.
Yeah, or I'm just going to leave it in factored form.
Okay.
It'll
Yeah,
help us
y
in the
times
next step.
1. Yeah.
Yeah, we'll get y times 1 plus natural log of x. Just multiply both sides by y. You know, it would be nice if we could get this all in terms of x. Because unlike what we were doing in Standard 8, where our original expressions were expressions defined in terms of both x and y, in this case, our original function is just the function in terms of x. Y equals x to the x power. So it'd be nice if we could find a way to write our answer y prime to be just in terms of x as well. So is there anything we can do here to replace this y with some x stuff? Morgan? Right there. Nora?
Could you substitute x and the x and the y?
You're right between the two Morgans in my vision lines. Sorry about that. And I also completely missed what you said.
Could you substitute the x to the x and the y?
You could indeed. Yeah, we could use the fact that y is equal to x to the x to plug that in for y here, say that y prime is going to be x to the x times 1 plus natural log of x. Or if you prefer, you can distribute out the x to the x term and get y prime equals x to the x plus x to the x times natural log of x. And there you have it. That is how you differentiate x to the x power. You have to be sneaky about it and do some implicit differentiation. Franklin, what do you think? Did that give us the same answer as just using the power rule or just using the exponential derivative rule? Doesn't look like it. Although, funny enough, it does give us what we would get if we took the sum of these two answers. Coincidence? Marty?
I think not.
You think not? I'll leave you with that tantalizing thought. Turns out it's not coincidence, but the reason why is because of the multivariable calculus chain rule, which I don't want to get into that. Take Calc 3 if you want to discuss why this is not coincidence. Dr. Ursula, are we going to have to know this and are we going to be tested on this? No. I just thought this would be kind of cool to look at. You know, fun little post-break activity. How do you differentiate x to the power of x? Especially because last week in office hours, actually a couple last couple weeks in office hours, this came up a few times. How would you differentiate this? And it turns out the answer is you can't just use the power rule. You can't just use the exponential derivative rule. You gotta be sneaky about it. So, any questions or comments before we move back into actual standard 10 stuff? Yes, Charlie.
Are we gonna get a joke of the day?
Oh, my goodness. After I finish asking for questions, you can have a joke of the day. I forgot all about it. Joke of the day. Surprise! This isn't how you differentiate at all. It was all a joke. Alright. But seriously, any questions before we move on to other things? Alright. Several people one day are asked to test the hypothesis that all odd numbers greater than 1 are prime numbers. So first of all, the mathematician reasons that, well, 3 is a prime number, 5 is a prime number, 7 is a prime number, 9 is not a prime number, therefore the hypothesis must be false. The physicist says 3 is prime, 5 is prime, 7 is prime, 9 is not prime, 11 is prime, 13 is prime. Hence, 5 out of 6 experiments support the hypothesis. Clearly, it must be true. The engineer says 3 is prime, 5 is prime, 7 is prime, 9 is approximately prime, 11 is prime, and so on. The computer science student reading the output from his screen says 3 is prime, 3 is prime, 3 is prime, 3 is prime. He needs to work on his code. The biologist says 3 is prime, 5 is prime, 7 is prime, 9, more research is needed. Psychologist claims 3 is prime, 5 is prime, 7 is prime, 9 is prime, but tries to suppress it. And finally, the politician says some numbers are prime, but the goal is to create a kinder, gentler society where all numbers are prime. Okay, so rest of today, I'm going to wrap up Standard 10. You actually don't have very much to talk about. Standard 10 is a pretty short standard. But if you remember, last week we were looking at differentiability. And the idea that if you have a function that is differentiable at a point, that just means that you can take f prime of a and it comes out to some finite number. So like f of x equals x squared is differentiable at 3 because you can differentiate, get y prime equals 2x, plug in 3 to get y prime equals 6, and that's a finite number. And what we said towards the end of class is that if you have a function that's differentiable at a point A, then your function also has to be continuous at A. So in other words, if your function fails to be continuous at a point, there's no possible way for it to be differentiable there. What about the vice versa here? If we have a function that's continuous at a point, does that automatically mean it has to be differentiable there? So in other words, must a continuous function, or let's write it this way, must a function continuous at x equals a also be differentiable? At x equals a. Or is it possible to have a function that's continuous at a point, but not differentiable there? What do you all think?
You can't have a function that's continuous. Like if it is possible to have a function that's not differentiable.
Even though it's
Even though
continuous?
continuous, yeah.
Can you give me an example of such a function?
Like if there's a cusp or a corner, like you were saying last time.
Or a so-called corner?
Yeah.
Yeah, okay. So what function were we looking at last time that had an example of that?
Oh, absolutely.
Yeah, absolute value. Yeah, so we could say the answer would be not necessarily, because if we look at, for instance, f of x equals the absolute value of x, which gave us this sort of V shape, there's a point on this graph where f of x is continuous. Well, it's continuous everywhere, but there is a point on this graph where it's not differentiable. So what point is that? Or at what value of x does this function fail to be differentiable? Okay.
X equals 0.
Yeah, at x equals 0. You could say f of x equals absolute value of x is continuous, but not differentiable at x equals 0. So why is this function not differentiable at 0? Other than the fact that there's a sharp corner there and sharp things are bad. What could we say about the slope of the function at, say, x equals 0? James?
The slope approaching it from the right and the slope approaching it from the left are different.
Yeah, we actually looked at this in detail last time, but we saw that from the left, this function has a slope of -1 as x, well, anywhere to the left of 0. Anywhere to the right of 0, this function has a slope of +1. So at 0, there's not a single slope that you would get. When we tried to set h approaches 0, not 6. Last time what we said, that when you tried to evaluate this limit, if you evaluated it as h goes to 0 from the left, you get a limit of -1. From the right, you get a limit of +1. So in other words, the slope from the left and right, or the slopes, I should say, from the left and right are not the same. Questions, comments, concerns? Okay, I can tell you all are looking tired out there. Time to give you all some problems to work on. So, if you look in your packet at the third page, and also the following page actually, I give you 7 different graphs of functions. All of which are functions, and all of which have a particular point A denoted on the graph. So what I would like for you all to do is for each of these 7 functions, see if you can determine whether or not that function is differentiable at x equals A. Where again, in order to be differentiable at that point, you need to have a slope, a single slope that exists at that point, and is a finite slope. You can't have an infinite slope, like a vertical tangent line, for instance. So go ahead, take a few minutes, and as always, I encourage you to talk to your neighbors, and see for each of these 7 functions on this page and the next one, do you think this function is differentiable at x equals A? And if it isn't differentiable there, why isn't it differentiable? Let's go ahead. Work on that for the next few minutes, and then we will reconvene as a class. While you all are working on that, I'll go ahead and draw these out on the board. Disappointing. I've been hearing all sorts of stories about the sickness. Oh, great. That's a fever tick. Okay. I can go right and get one. Okay.
So just right there.
Are you saying that this one is differentiable?
No. I'd say no, just because it's a vertical line right there.
But also, you can't tell if it's actually going straight up or if it's just getting
That's true.
I would say you missed it. But if you straight up, yeah, maybe.
I'm not sure.
Why are clusters?
What's a custom? Nope. Custom. That is a custom. That is a corner. The difference is the same idea that the slopes from the left and right are going to different things, just that for a custom, plus or minus infinity died on your side. Whereas for corner, it's just like, I don't know, something like 1 from the left and -1 from the right.
So for this one, the slopes on the left and right would be different as you cross the
Nothing necessarily. True, but as you get closer and closer to A, they're approaching the same value. What value is that? Well, f prime of A, but what would f prime of A be for this particular graph? Yeah, it'd be a slope of 0. On the left, it gets closer and closer to 0. Positive numbers getting closer and closer to 0. From the right, it'd be negative numbers getting closer and closer to 0. So you could still say that the limit is 0 on either side. What's up?
So on this one, is it actually going straight up or is it just actually going straight up?
Let's say it's actually going straight up for just a split second. I misread. See, Socrates, I'm used to thinking immediately, oh, because of right. That's because I was a pre-med student once upon a time.
What changed your mind?
The fact that I decided I didn't actually want to go into medicine, and that's more something my parents wanted for me. It was scary, it was hard, I needed to do something safe and easy like math.
I wouldn't necessarily say it's easy.
Oh, I wouldn't either. And actually, that's why I did a psychology major first for a couple of years, and then kind of decided to add math on top of that because reasons. That's me more outside of class, and I can tell you more about that story.
But this one is.
Yes, for the first one.
Yes.
Take about one more minute, and then we'll come back together as a class and take a look at these.
Oh yeah, I got that.
Yes, but I don't know. So sleep with
Alrighty, let's come back together and take a look at each of these. Alright, we're going to vote on each of these by a show of thumbs. And I don't want to see any of these, and I don't want to see any hands not doing anything. For each of these, I want a thumbs up for you think it's differentiable at a thumbs down for you think it's not differentiable at A, and a thumb sideways for I'm hedging my bets. Then I'm not feeling very confident as to what the answer is. All right, remember, thumbs up differentiable, not differentiable. Start with this first one. On the count of 3. 1, 2, 3, vote. Most of you hands up. All right, looks like everybody thinks this one is differentiable. Emerson, what does it look like the slope would be at x equals a?
It looks like it would just be whatever the y value is.
That would give you what f of a is, but what would f prime of a be if we were to take the slope of this tangent line right here? So what would you get if you tried to take a slope of just a plain old flat line?
It would be 0.
Yeah, I would say in this case, yes, f prime of a is going to turn out to be 0. So this one, perfectly fine. It's differentiable at a, has a derivative of 0 because the tangent line, if you draw it out, is perfectly flat at that point. And if you have a question, or are you just going to answer to it? Let's do this one next. By a show of thumbs, 1, 2, 3, vote. Okay, this one's a little bit more controversial. Looking around. Katie, why do you say thumbs down?
Because when it's approaching it from the left and the right, is it going to be a different slope?
I actually think it'll be the same from the left and the right. In fact, if we were to try and draw out a tangent line, I think we would get a single tangent line here. But as a question to the class, what's up with this tangent line at x equals a? What would we say the slope of that line is, Kate?
It's undefined
Why is it undefined?
because it's a vertical line.
Gadzooks, so the rise over run would be, it's all rise, no run. You'd be like dividing by 0, so to speak. Yeah. So in this case, we would say no. F of x has a vertical tangent line at x equals a with undefined slope. Yeah, anytime your tangent line is horizontal, that just means you have a slope of 0. But if you have a tangent line at your point that is completely vertical, that would be saying you have, say, an infinite slope. In fact, if we were to try and use this limit definition here to compute the derivative at that point, what we would get is something like 3 over 0, or we get a limit that's going to positive infinity in this case. So this would be a case where the limit turns out to be something that's not a finite number. Franklin.
How did you know or how did you get to where, how did you know it's a vertical tangent, not a horizontal tangent?
For the
second one.
For the second one? How did I know? Well, it's because I purposely tried to draw it so that it would have that effect. Let's see if I can do a better job of actually drawing it here. Yeah, something like that. Because if you try and look at any point on your graph and you try and draw out what does the tangent line look like, remember you're trying to kind of draw a line that sort of matches up with what the slope of the function looks like at that single point. So that here, for instance, it would be here, that just sort of skips off the surface of the function, so to speak. And this point here, we would have a slope that looks something like that. So that the slope of the line matches up with the slope of what the function would look like there. And here, if we tried to do the same thing, it would just be a vertical line. Another way to think about it would be if you were to zoom in really close on the graph of the function, like put this function under a microscope, so to speak, and look just at that point itself, all that you would be able to see there if you zoomed in far enough would be something that looks just like a vertical line. Similar to how if you zoomed in really close at this point, what you would see is something that looks very much like a horizontal line. All right, next function, this one in the bottom left here. By a show of thumbs, is this differentiable? 1, 2, 3, vote. Let's see, lots of thumbs down. Nolan, why do you say no?
Because it's a corner.
Gadzooks, we have a corner. And so for very similar reasons to why absolute value of x wasn't differentiable at 0, this function is going to be non-differentiable at a. The slope is going to be different coming from the left and the right in this case. So I'm going to say no. There's a corner at x equals a, i.e. the slope is different from the left and right. So this one sort of looks like a seagull, so I'm going to call this the seagull function. By a show of thumbs, is the seagull function differentiable? 1, 2, 3, vote. Gabe, why you say no? That was a good English sentence, by the way. Why you say no?
Like cusp again. It's not actually like function.
Say that again?
It's a cusp again.
It's a cusp.
Yeah.
Is that different from a corner?
Kind of, but not really.
Elaborate.
I guess like corner you get like two lines basically with constant slope. With the cusp you got like curvy slopes.
It's sort of related to that. What I would say is that you have something where the slopes are different from the left and the right, but if you look, what's going to be the slope from the left? I would say it's getting close to, it's getting more and more and more negative. Oh, I forget, you all are flipped from the way. Let me face the same direction. It's getting more and more and more negative, so I would say from the left the slope's going to negative infinity, whereas from the right it's becoming more and more and more positive the closer you get to A. So from the right you would get a slope approaching positive infinity. So I would say in this case that no, there's a cusp. At x equals a, where a cusp is going to be a point where the slope is different from the left and right, and the slope is going to be infinitely large on both sides. So on one side the slope's going to positive infinity, on the other side the slope's going to negative infinity. So the slope is different from the left plus right, from left and right, and is infinite. Whereas with the corner, your slope is different from the left and right, but at least they're finite values on the left and right side. Looks here like from the left you have a slope of about, I don't know, +1, from the right maybe a slope of -1. On this case, the slopes are different from the left and right, but they're also infinite values on both sides, rather than just having these finite numbers for the slope on the left versus the slope on the right. And that is the difference between a corner and a cusp, so to speak. Questions, comments, concerns? All right, next function. Going to the other one to the back page. This function that's doing something wonky here at x equals a. Show of thumbs. Is this differentiable at a? 1, 2, 3, vote. Caleb, why do you say that's not differentiable at a?
Because the function's not continuous.
And if it was differentiable, it would have to be continuous?
If it was differentiable, it would have to be continuous, yes.
Yeah, we have a theorem from last time that says that if you have a function that's differentiable, it has to be continuous. Well, this function is clearly not continuous at x equals a, therefore it cannot be differentiable. F of x fails to be continuous at x equals a, hence is not differentiable. By the way, Caleb, why do we know that this is not differential, or let me rephrase. Why do we know this is not continuous at a?
Because the limit as x approaches a from the left does not equal the limit as x approaches a from the right.
Yeah, it fails that third condition of continuity, it fails that, but it also fails the second condition of continuity, where the limit as x approaches a of this function does not exist, since the limits from the left and the right are not the same. This time for the original function rather than from this derivative limit. So we can say that the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of our function. Next one, we've got this sort of graph, but with a hole right here. Show of thumbs, is that differentiable at a? 1, 2, 3, oh. Emma, why do you say no?
For the same reason as the one before, it's not continuous.
It's not continuous today. Why isn't it continuous today?
Because f of a does not equal the limit.
Yeah, exactly. So we could say once again, f of x fails to be continuous at x equals a. Because in this case, the limit as x approaches a from both sides does exist and is equal to each other. So the overall limit exists, f of a exists, but they're not the same value. And finally, our last one. Same thing, but I took away this point right here. 1, 2, 3, vote. Anna, why do you say that one's not differentiable today?
Because nothing equals a.
Nothing. Nothing equals a. Doesn't a
There's
equal
no
itself?
point at a.
Oh, there's no point at a, so f of a does not exist? Doesn't look like it to me. And if f of a does not exist, then you can't have continuity. And if you don't have continuity, then you can't have differentiability. So, for the third time, f of x fails to be continuous at x equals a because f of a does not even exist for this particular function. Any questions or comments about any of these? So with that in mind, I tried to kind of give a bunch of different examples that kind of illustrate all of the main ways a function can fail to be differentiable. So I thought it might be helpful if we summarize with a list. What are some common ways that a function can be not differentiable at x equals a? So in other words, some common reasons looking at the graph of your function that you can determine, hey, this thing isn't differentiable at a. What gives? So what can we put on our list? What would be one common way, do you think, that a function can fail to be differentiable at a point? Eden?
Vertical slope.
Yeah, if the tangent line, if you have a vertical tangent line or a sort of a slope that's going to infinity, let's say, that would definitely fail the is finite part of the f of x is differentiable. Got to underline differentiable. So one common way is f of x has a vertical tangent line at x equals a. What else can we throw up there as maybe a common reason? Aiden?
F of a or the limit as x goes to a does not exist.
Okay. I'd categorize those both under the same heading of f of x fails to be continuous at x equals a. But yeah, we could say f of x is not continuous at x equals a. Which, as we've seen, can happen for a variety of reasons. You can have f of a fail to exist, you can have the limit as x approaches a fail to exist, or you can have that both of these things exist but don't come out to the same value. What else? I have two more that I'm thinking of. Ty?
A corner.
Yeah, we could say that f of x has a corner. At x equals a. Like the absolute value of x. Something where the slope from the left and the slope from the right at your point are not the same value. And finally, which one are we missing? Morgan?
A cusp.
Yeah. Or a cusp, where you have a different slope from the left and the right, and you have infinite slopes on both sides. There are other ways for a function to fail to be differentiable that are not these four values. But these are kind of the four main ways that you can have non-differentiability. This corner, a cusp, a lack of continuity, or a vertical tangent line. I'm going to tell you exactly what's on the quiz for Wednesday. On Wednesday, I'm going to give you I'm going to give you a graph of a function. And it's going to be up to all of you to tell me where are all of the points on this function where the function is not differentiable, and why. Meaning at each point that you claim, hey, this thing's not differentiable there, what's going wrong? So you're going to have like one big graph where there's probably multiple points where you're lacking differentiability, and you need to kind of point out all the points where one of these four conditions happens. And basically be able to say, hey, this is not differentiable here because it's not continuous, and it's not differentiable here because you have a vertical tangent line, etc., etc. So that's what's going to be on Wednesday's quiz. Sound good?
Yep.
Groovy. Congratulations. We have now talked about how to differentiate every function we're going to be differentiating this semester. But what if I told you this calculus is not all about differentiating things? Sometimes it's about anti-differentiating things. Which is like taking a derivative, except you're going backwards. And that is going to lead us to standard 11. Here you go, Nathan. Pass these out to your classmates, please. One, two, three, four, five, six.
Thank you.
So here's the scoop. Standard 11. Standard 11 and 12 are going to be focused on, instead of saying, hey, here's a function, find its derivative, we're going to be working backwards. Meaning we're going to be looking at the question of, given a function, find all other functions whose derivative is equal to your original function, which is called taking an antiderivative. So with the time we have left, what I would like for you all to do is I would like for you all to work your way through the first page on your own of this packet. So go ahead and take a few minutes, talk to your neighbors, and what I want you to do is we're going to take the function f of x equals 6x plus 2, I want you to find 3 different functions for me that all have a derivative of 6x plus 2. See what relationship do these 3 functions all have with each other. And then finally, how many functions are there, do you think, that have a derivative of 6x plus 2? I'll give you a hint, there's at least 3 of them. Not a trick question. So go ahead, take a couple minutes, work your way through the front page, and as always, talk to your neighbors and flag me down if you have any questions. Oh, it's supposed to be a plus.
It's basically just all of the same. Because if you think about it, like, we're gonna say the derivative of 6x plus 2.
Yeah, that's like.
And then the derivative of any constant is 0. So it's gonna always be just at the beginning. Mhm.
Oh, you just wrote it. Oh wait, no, that actually
I'll give you a hint. If you're having trouble finding 3 functions, your 3 functions do not have to be super different from each other, let's say. They can share some similar properties, perhaps.
Texted me.
Who's texting?
Our coach. I know, how dare he. Showing up early.
He's
I
in the
told
same
him
exact one every
50,
time with every customer.
8:45.
Yeah.
Yeah, that's exactly right.
Text him back. Dr. Gerstle does not appreciate this.
Dr. Gerstle says we'll be out at 8:30. Shit.
Dr. Gerstle is going to hold us until 8:55 just because of this insolence.
Who's this supposed to be?
Who's this coach you speak of?
Who is Mr. Kurtz? Yeah.
Coach K.
Are you able to find some functions you like? What you come up with?
Just feels so cool.
Like, yeah.
Oh, so you're saying you're infinitely many constants of equation. Okay, gotcha. Sounds like the constant equals plus or minus thing. Sounds like you plug in. Okay. That's plus.
Oh, right.
That does not work. But I.
Any number. I feel so bad.
That's the right idea. Alright, I'm gonna cut you off here. I know some of you are still thinking. So here's what we're gonna do. I want you all to take some time between now and Wednesday's class to think some more about this. In Wednesday's class, we're gonna have a quiz on Standard 10 to start things off, and then we will come and talk about these questions as a class. See what you all have noticed. And then that's gonna lead us into our definition of the indefinite integral of a function. And we're gonna get all warm and cozy and start talking about families in here. Families of functions. Have a good one, everybody. See you all on Wednesday. Welcome back to Hillsdale.
Oh, yes.
Take care.